But I wanted to finish up a couple things in the eye, the visual system. So there's this notion of the dual visual system. And in fact, we do have sort of two distinct visual modes, pathways. I don't know what the right word to describe it is. They use system, dual visual system. You have to pardon my nose now. Kicking the last of it out. There's the scotopic system. And I've already sort of said this earlier in this lecture. This is a high sensitivity, low light system composed of the rods. So you can think of this as a large receptive field. When we were talking about receptive fields in sensory neurons, like the back versus the fingertip. All right, so this is a large receptive field. You see here it's approximately a square millimeter of retina. That doesn't seem big, but it's huge. Because of that, a photon falling anywhere within that area is going to set that this neuronal tree off, this neuronal pool. So we have many, many rods that come down to a little bit, they converge. This is a convergent pathway that converge on significantly fewer bipolar cells and then all go to a single ganglion cell. This ganglion cell is of a type called an M cell. M is for magno or big. It is certainly that histologically, and it integrates the information of a wide range of these cones. On the other hand, so this is responsible for shadows and dim light, giving us information about motion and the general shape of an object that would be in the peripheral vision. These rods are mostly on the peripheral vision, so in the part of the retina that is not in the fovea or the macula. Okay? Then in the macular region, we have this photopic system, and there's almost a one-to-one correspondence between a cone and the bipolar cell and its corresponding ganglion cell. And these ganglion cells are P cells. P stands for parvo, and that means that's for small. All right, parvo. So this is going to give us information about fine details, the edges of objects. This is going to give us our high resolution. And in fact, there are three types of cones, as many of you are probably aware, the red, green, and the blue cones. So they are sensitive. Their sensitivity maximum are at three different wavelengths of light in the visual light spectrum. All right, the photopic system. So a much smaller receptive field, okay? Because of that, less sensitive. All right. So, and this is just sort of belaboring this concept of retinal convergence. This is I've said this before about the information processing that happens within the wall of the retina itself. There's this retinal convergence of 130 million photoreceptors that are being monitored by a single magno ganglion cell with 6 million bipolar cells. However, there's also a horizontal integration, and I have a couple other slides that expand upon this a little bit more, but I've cut them out for the sake of time. And these are mediated by both the horizontal and the amacrine cells. Horizontal at the photoreceptor bipolar interface, and it's these horizontal cells which are responsible for mediating the activities at these junctions, at these synapses. And then the amacrine cells have a similar function at this interface. And so what that is, for example, say Killian here was a photoreceptor. You're all photoreceptors, and he absorbs some frequency of light. The job of of the brain is to figure out what the totality of the image is. So integrating information from all the adjacent, from all of the photoreceptors in the class. So part of that information processing is simply sharing information, his state of stimulation, with his nearest neighbors. All right. So he would talk to Becky and Haley and Anna and Sonia, for example, and say, I am seeing light right now, and I'm a red cone, whatever. And so if they're seeing red as well, if Sonia's seeing red, then we know that he's not on the edge. Or if we know Sonia's red and Becky's red, then Killian is not on the edge. However, if Sonia is dark or blue or whatever, some other thing, then it can be interpreted that he represents, and the two of them represent, an edge in the image. All right. So this type of signal processing is happening through horizontal integration, not just vertical integration in terms of convergence, but this horizontal information sharing. Okay. So that's that. And then the last point that I wanted to make here was about the visual pathways and depth perception. So depth perception, our ability, for me, for example, I'm picking on Killian, to say that he is maybe 10, 12 feet away from me, that's because I am able to judge his depth. That's by triangulation. My eyes are separated by whatever this is, about 3 inches, 3.5 inches, or something like that. And so that gives me, I see the relative shape and shadow of the contours of his body with my right eye, and then similarly I can compare that with the same sort of information from the other eye, that those informational pathways have been mapped into the visual cortex, and I'm able to come up with a sense of distance and direction. And this is by comparing shape, proportion, but also these relative angles, the way they describe it here, alpha and beta. Yeah, so the notion of relative disparity between the angles alpha and beta. I'm not going to go through that in depth because it's not something I'm actually going to test you on, but it's there. It's interesting triangulation. So the visual pathways, we have information from the back of both retinas coming to this optic chiasm. The optic chiasm is kind of similar to the corpus callosum in the brain, or the in the spinal cord it would be the commissures, the anterior white commissure, anterior and posterior gray commissures. It's where we have decussation of some of the fibers that is going from one side to the other. Okay, so in this chiasm there's some decussation of fibers. So here on this optic tract coming out of the optic chiasm, this optic chiasm is right where, right here is where the pituitary gland, the hypophysis, is right here in the infundibulum. The hypothalamus is deep to this, wraps around these optic tracts, wrap around to the lateral geniculate nucleus, where there's going to be a synapse. This is going to have projections into the suprachiasmatic nucleus, and then here, importantly, into the superior colliculus, where this is going to coordinate visual information with efferent output, body motion, motor response. But then coming out of this lateral geniculate nucleus, there are these projections, these optic radiations into the visual cortex of the occipital lobe. Ironically named because occipitus means occluded. It's the same, unseen, because it is the furthest away from your eyes. You cannot see it, but ironically it's where your visual cortex is found, in the occipital lobe. All right, so that's all that I wanted to say there. Oh, well, I guess the last point is this information that is the superimposition of the two visual fields from the left eye and the right eye is where you have binocular vision. There is portions of the periphery on either side that you don't actually have binocular vision. It's very hard to judge depth perception in your extreme periphery. Okay, onto the ear. I'm going to give you a little bit of anatomy. I really don't want to shortchange the ear here. There is some stuff I got to cover. The ear is divided into three regions, the external, middle, and internal ear. The external ear, there's not a lot of anatomy that I need to point out here for our discussion, but we call this the external acoustic meatus. This is your ear hole. At the end of it, there is this tympanic membrane, all right, and that's kind of like the drum head, the head of a drum. It's a thin membrane that's able to vibrate. You're probably all familiar with that. Attached to that are a series of three ossicles, the auditory ossicles, three tiny little bones, the stapes, the incus, and the malleus, heading from right to left here. These bones are housed in what's called the petrous temporal bone. So all of this is part of the temporal bone. This part of the temporal bone is called the petrous temporal bone. Petrous, just like you are, I don't know if there are any like saltpeter or rock salt or any people who know anything about the Bible. Simon was named Peter because you are the rock upon which I will build my church. Peter means rock. Petrous is the rocky, it's the rock in your head. It is the densest bone in the body. It's the hardest bone in the body. And because of that, it is, well, no, it's causality here. So because there are such delicate structures, the three tiniest bones in the body, the delicate structures of the inner ear, they are housed in this highly dense part of bone called the petrous temporal bone. For those of you who are going to get to go to medical school and do some dissection, most anatomy labs don't have you dissect the middle ear, but you can if you want to. And I'll tell you right now how to do it. It's kind of fun. When you look at the petrous temporal bone, it's an almond-shaped ridge inside the middle cavity of the brain case. And if you take one of the electric bone saws and you just score along the edges of that almond-shaped petrous temporal bone, sort of define the edges of that almond. You take some rongeurs, basically bone-snipping, wire cutter-looking things. You stick them in those grooves and you just lightly crack. The top will come right off that petrous temporal bone. So on the back side of this clivus petrous here, you would put a score and then another one along here, clip it off, and this whole thing will just pop right off, and you'll see that middle ear and inner ear. It's a pretty dramatic thing to do when you're in medical school. You'll impress the socks off your instructor there, so it'll be fun for you to do. Anyways, the stapedius inserts into this thing called the oval window. So all of this region here is the middle ear. The middle ear connects with the nasopharynx via this eustachian tube or auditory tube or pharyngotympanic tube. Those are all three of them synonyms for the same thing. This is responsible for normalizing the pressure on either side of that tympanic membrane. The doorway then to the inner ear from the middle ear is this oval window, which leads into the bony labyrinth of the inner ear. Pardon me. Yeah, we'll talk about the inner ear more in a moment. External ear fills with wax. Don't stick Q-tips in there. If you want to get the earwax out, stick some mineral oil in there. You can tell a lot about the ear just by looking in there. You can see here's one with fluid inside. Here's one with an acute infection. Here's somebody who blew their eardrum. Here is a perforation that has been artificially put in the ear with a little plastic cannula there, and that is for children who are prone to otitis media. I'm sorry. That is for people who have a buildup of fluid in their ear and need it to drain.
So be careful with the Q-tips. Don't stick a Q-tip in your ear. Yeah, that looks uncomfortable. It happens a lot. Yeah, the only thing you should stick in your ear is your elbow, or maybe a little bit of mineral oil if you got this wax in there and you need to get it out. The motion of your jaw, like this, is actually pushing that cerumen, that wax, forward out of the ear. Healthy earwax will just naturally fall out in quantities that you won't be able to see. Yeah.
So is that like if you had it in there and you bumped into something?
This happens more often than you'd think it would. People just are going for it. They think there's something in there, and bam, because they have been too aggressively cleaning their external acoustic meatus. They've irritated it. They've thrown off the microbiota in there, and it becomes itchy, and so they think there's something in there, but there's not, and they end up just...
What does that feel like?
Couldn't tell you. Not good, I'm sure. I meant to... I just wanted to show you the picture of this. This is kind of cool. It's a cool picture. I'm not going to talk about otitis media, but here is a light in the external acoustic meatus lighting up the tympanic membrane. They stuck a camera up the pharyngotympanic tube, so through the eustachian tube in the mouth. Get this dramatic picture here. Here we see the stapedius inserting at the oval window. The stapes, I shouldn't say the stapedius, this is the stapedius muscle. There's the tensor tympani, where would that be? Here it is. The tensor tympani muscle, which inserts on the malleus, and the stapedius, which inserts on the stapes. These are muscles that when there's a loud noise, they tense up and minimize the vibration. They dampen the vibration of those bones to try to protect your hearing. All right, the cochlea first. We're going to talk about the two separate systems. There's actually three separate systems in the ear. 1, 2, 3. First, hearing. So hearing is achieved through the mechanism of the cochlea, this sort of snail shell thing that we have. And so here's a picture of it. We're going to transect it, and we have this bony labyrinth that spirals its way up to the tip and then turns around and spirals its way back down. That bony labyrinth starts at the oval window. So this tube is contiguous with this one here, 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 and then it wraps around the top of the cochlea and comes back down here, all right, to the round window. And we'll see the significance of that later. Embedded in this bony labyrinth throughout the inner ear is this membranous labyrinth. This is all soft tissue membrane right here. This top part that starts at the oval window is called the vestibular duct because it communicates with what we'll call the vestibule in a little bit when we get to that part. Gets to the top, turns around, and becomes the tympanic duct. So all of this here is what we call the tympanic duct. They are contiguous. If you were a tiny little creature, you could walk up one and then turn around and come back down the other, okay? So the vestibular duct becomes the tympanic duct. In between the two of them, we have this cochlear duct here. The cochlear duct is where the hearing organ is, and that hearing organ is called the organ of Corti right here. We're going to see it in much more detail in a moment, but there are these ganglionic cells that have sensory neurons that project up to these organs of Corti in the cochlear duct. All right, and the cell bodies of these what are going to be called hair cells, these sensory cells, form what is called the spiral ganglion. So here's a spiral ganglion, here's one, here's one. There are all of these spiral ganglion that are embedded in the bone of the cochlea. They're dendritic processes extend out into the organ of Corti in the cochlear duct and get stimulated by sound. And we'll see how that works in a bit. Does that make sense? All of these then coalesce to form what's called the cochlear nerve. The cochlear nerve. It is one branch of cranial nerve 8. Cranial nerve 8 is actually a combination. It's a combination of the cochlear nerve and then the vestibular nerve. Together, cranial nerve 8 is called the vestibulocochlear nerve. All right, but they're carrying totally different information from totally different structures. Okay, so you can see here how we have the stapes at the oval window connecting to the vestibular duct. It goes around, turns the corner, comes back down towards the round window. And we'll see what that does in a moment. But first, I want to zoom in on this cochlear duct. So it's a membrane-delimited canal. So on the top side here, on the superior aspect, we have this vestibular membrane that separates the vestibular duct from the cochlear duct. On the bottom, we have the basilar membrane, which separates the tympanic duct from the cochlear duct. And then we have this structure here, which is called the organ of Corti. The organ of Corti has another membrane. So there's 3 canals, and there's 3 membranes. This membrane is called the tectorial membrane. The tectorial membrane does not separate anything. However, when sound is going through what's called the perilymph, the fluid that is in the tympanic duct and the vestibular duct, it's going to vibrate this basilar membrane. These hair cells are going to interact with this tectorial membrane. It's going to knock over these the projections, the hairs on these hair cells, and that's going to open up mechanically gated channels. That's going to cause a depolarization and a signal to come out. Okay, you see how that works? So these hair cells, there's 2 groups of them. There are these outer hair cells and a single line of inner hair cells. We'll see some striking images of those soon. Here you see the spiral ganglia with their projections out to the organs of Corti. Those are the cell bodies of the sensory neurons. Yeah?
So is the vibration filtered first by the bones in the middle ear?
Yeah, we'll see what happens in a minute. Now, filtered is probably not the right word, but there is the bony structure of the cochlea is a frequency filter, and we'll see how that works in a bit. So here is a scanning electron micrograph of the hair cells. So the tectorial membrane has been removed here. We can look down onto the organ of Corti. Here are the outer hair cells. Here's the slope. Here are the inner hair cells. And back here would be the center of the cochlea and the spiral ganglia that are connected to each of these. That's a colorized image, obviously. All right, so how does it work? They're in outer space. Nobody can hear you scream. But here on Earth, there's air, and sound information gets, vibrational information of sound gets encoded in compaction and expansion of the molecules in air. All right, and that vibrational pattern, it's just like smacking the water, and you see waves ripple out in the water. It's the same thing happens in the air when a sound happens. That air vibration, there's a certain wavelength, a separation in the peaks. That's going to give you your frequency. Frequency is just the inverse of wavelength. And then there's amplitude. And so wavelength is related to the pitch, like how high or low the pitch is. And then amplitude is related to the power, which we interpret as volume, the power in that wave. How loud is it? Okay? So the higher the amplitude, the louder the wave. There's some really exciting things I want to talk about, and I hope I get to it about hearing here in a bit. So we see the movement of sound waves impinging on the tympanic membrane, vibrates the membrane. The malleus or mallet, the hammer, malleus, mallet, strikes the incus or anvil. Incus means anvil. And then translated to the stapes or the stirrup, which inserts into the oval window. This sets up a vibration in what's called the perilymph, this fluid that is filling the bony labyrinth that's going through this vestibular duct. And it's going to vibrate because of the particular frequency of vibration and the spiral pattern of the cochlea, the logarithmically, exponentially reducing spiral of the cochlea. That frequency is going to have a sympathetic vibration in the basilar membrane or the vestibular membrane this is the vestibular membrane, in the basilar membrane at some certain point along the course of the cochlea. And that vibration is then going to be released, that pressure is going to be released at the round window. So when this is going in, this is going out, and vice versa. All right, so the pressure remains constant in this container, but the vibration is going to perturb that basilar membrane at a certain specific point. There is then what's called a labeled line, the labeled line code, and our brain interprets frequency vibration or stimulation at any point in this basilar membrane as a specific frequency. Okay? We'll see a picture of that in a bit. Here we go. So stapes moves in, there's a vibration, and because of the speed of that vibration, the frequency, it's going to bend the membrane here. Those hair cells are going to interact with the tectorial membrane, and this is pushing the round window outward, and then stapes moves outward, and basilar membrane deviates this way, and round window gets pulled in. Okay, do you see why there's the necessity for having this membrane covered? The round window has its membrane covered. This round window to let the pressure off. Fluid is incompressible, relatively. So, and the point being here, so we see the entire frequency range that the human hearing spans along this basilar membrane. In the hair cells themselves, here we have a potassium-gated channel, that a mechanically gated potassium channel closed. It is connected via these linking proteins to the adjacent hair nearby, and when you tip this whole line of hairs over, this linker protein is going to rip open the door and allow potassium to flood in. See how that happens? Pretty ingenious. You can imagine that a really loud sound, that too vigorous a vibration in the basilar membrane could easily injure this system. This is why loud sounds are chronic exposure to loud sounds is destructive to your hearing. So the visual pathways, the auditory projection pathways, we have this labeled line code coming off the cochlea going through cranial nerve 8. It's going to first synapse in the cochlear nucleus of the midbrain, and then it's going to send fibers up to the inferior colliculus. So you'll remember when I talked about the visual pathway just a few moments ago, we saw there was a projection to the superior colliculus, and this is the pineal gland right here. These four are called the corpora quadrigemina, the four quadruplets, the body of four quadruplets. The two top ones are for vision, the two bottom ones are for hearing. So first, the cochlear nucleus in the medulla up to the inferior colliculus. Synapse there, and then projections go all over the place. We get efferent projections to the cranial nerves, but we have ascending fibers that come up to the geniculate nucleus in the thalamus. Remember, so for sensory information to register in your brain, what has to happen? You have to have synapse in the thalamus. Okay? You have to have synapse in the thalamus. So here it is. From the thalamus, you get a projection into the temporal lobe, temporal right along the side here. So, yeah. And we have the same, this, it's not a somatotopic map, but it is an auditory map of frequency sounds that you see in the cortex there. Is there anything else I want to say about hearing? No. I don't think so. So, yeah. Please protect your ears. I was such a foolish youth going to all those rock concerts for years and years. A quiet library is, we measure sound, the intensity of sound in decibels. It's a logarithmic scale. So here about 30 decibels is a quiet library, a soft whisper. And the lowest audible sound is just a little bit below that. It's near 0 decibels. 0 decibels is not silence. You can go below that, but it is a very quiet sound. And we call it 0 because that is the bottom of our ability to hear. Okay? And moving up, quiet office, living room, light traffic, air conditioner. All right. If you're in busy traffic, that's around 70 decibels. If you are there all day, every day, you could have some hearing loss. If you're in a subway for more than 8 hours at a time, you could, on a chronic basis, or an alarm clock at 2 feet, factory noise. These people have hearing loss. If you, at 90 decibels, a lawnmower less than 8 hours can lead to hearing loss unless you wear cans. Put those hearing cans on yourself. If you use a chainsaw any more than 2 hours at 100 decibels, plan on having some hearing loss with time. I love this. Heavy metal rock concert, immediate danger. Yeah, any of you who are into sandblasting or like to chase storms, you will have some danger to your hearing. Gunshot, jet planes, immediate danger. If you are unwise enough to be on the launch pad of a rocket, you are going to lose your hearing. So this is incredible. This is incredible. There is nothing else that I can tell you about your body that has the same magnitude of dynamic range of sensitivity. So if you look, people certainly go to heavy metal rock concerts all the time. If you look at the range of human hearing that humans regularly find themselves in, that's over a trillion-fold power range. A trillion-fold power range. Imagine if you had a trillion-fold power range in terms of your ability to feel touch. Okay? Like the lightest touch that you can perceive, and then increase that by a trillion-fold. That's extraordinary. What about intensity of light? A single photon is the least that we can perceive. Magnify that by a trillion-fold on a single sensory receptor. You would burn a hole through the back of your head with that. Okay? The fact that humans can hear this amazing power ratio, it's astounding. The amplitude ratio here for that we're talking about is 1,000,000-fold. That's unbelievable. Like the amplitude, then 1,000,000 times higher. That's stunning. Okay, so hopefully I've impressed upon you the danger of exploring that extreme upper end. So here is this wise person listening to the sound of the earth rotating with happy inner and outer ear hair cells. And then here is this guy also, I'm sure, very blissfully rocking out in front of his double Marshall stack, but here's his inner ears, and with time, he's only going to be able to hear you through a double Marshall stack because it's damaging those hair cells. Protect your ears. All right, we've got 10 minutes to talk about your sense of gravity and your sense of 3D rotation. So the inner ear is this bony labyrinth. It's this bony labyrinth. I talked about that with the cochlea. And I said there's this membranous labyrinth inside, which we call the cochlear duct. And the organ of Corti is embedded in it. The membranous labyrinth is filled with a fluid called endolymph. On the outside of that is the perilymph, between the bony labyrinth and the membranous labyrinth. Okay, this is just a schematic. So the rest of the ear, so here's cochlea, here's hearing. The rest of the ear has two functions. There are this vestibular system and then the semicircular canals. Okay? The semicircular canals are going to give you your sense of rotation in 3 dimensions. I should have brought in my model. I have a model of the inner ear. These 3 loops amazingly, stunningly, staggeringly confirm the fact that we live in 3 dimensions because each of those loops are disposed orthogonally 90 degrees to one another so that they perfectly lay within the 3 spatial planes, x, y, and z. All right? Or x, y, y, z, and x, z. Those are the 3 planes. X, y, and z, whatever. The vestibules, the utricle and the saccule, these are responsible for your sense of gravity and acceleration. Of course, these are the same thing. Gravity is acceleration, and it is the vestibular system that's responsible for giving us that sense. So let's see what this is. These are also, this information is conveyed again by hair cells. You can see how the cochlea and the utricle and saccule and the crista ampularis of the semicircular canals are all related. They use the same basic structure, same basic structure of these hair cells. So they're going to give us information about the direction and strength of a mechanical stimuli. Here's a colorized electron micrograph of them. All right, so first, the crista ampularis. I want to show you. Here is one of these semicircular canals. It's giving us information about rotation in space, all right, our relative orientation in space. And right here, the functional unit is the crista ampularis. Let's look at it closely. Crista ampularis, 3D rotation in 3 dimensions. We have this crista, which is a sort of crest or a lump. It's got the hair cells embedded in it, and with the hairs projecting out into this bit of jello called the cupula. It's this gelatinous mass called the cupula. And when you're moving along the plane in which one of those semicircular canals finds its axis, that fluid that is in that semicircular canal moves along with the body, right? Moves along with the body and displaces that cupula either in whichever direction that fluid is flowing, so either this way or this way, all right? When that happens, it's going to stimulate these hair cells. Now, this structure is a little bit different than you're used to. We have the stereocilia, they're called stereocilia, and then one special hair called the kinocilium. Kinocilium. When the stereocilia are displaced in the direction of the kinocilium, there is a stimulation of the hair cell. There's a stimulation. When they are displaced in the opposite direction, there is an active inhibition of that hair cell. Okay? And when they're not moving, there's no effect. So This direction is stimulation, depolarization. This direction is active inhibition. All right. Saccule and the Utricle. Now, so we've done the semicircular canals, the cochlea, and it's these last two pieces here, the saccule and the utricle. These structures are going to give us our sense of gravity and acceleration. Are you, not are you moving, but are you changing the velocity of your motion? Okay, that's what acceleration is. And the way this works is there's this macula, a patch in the saccule or the utricle that has this gelatinous material on it, some more, quite similar to the cupula of the Crista ampularis, all right, that gelatinous thing those hair cells are embedded in. These hair cells are stuck up into it. On top of it is this large structure called an otolith. An otolith, oto, ear, lith, stone, an ear stone, an otolith, is made up of all these tiny crystals that are called statoconia, which are tiny little crystals of calcium carbonate. Okay, and here we have a colorized image of statoconia that are embedded on top of this gelatinous material on the macula in the utricle and the saccule. So the way I describe this is I have a grandmother-in-law. My wife's grandmother is from Wisconsin, and this woman makes what she calls her prize-winning 7-Up salad. This is a kind of repulsive jello, lime jello, made with 7-Up. And on top of it, she puts whipped cream, bananas, and shredded cheddar cheese, because it's got to have some cheese in Wisconsin. It's got all this mass on top of this green jello mold. And she walks in with her 7-Up salad with little American flags, toothpicks stuck in it. And the top of it is going like this. It's vibrating like this, because there's all this mass on top of this jello. That's what this otolith is for. It's to give mass to the top of this, so that when you tip your head back, okay, when you're changing your orientation, and the acceleration due to gravity is going to pull this otolith back. It's going to stimulate these hair cells, and this receptor output is going to increase. All right. Basic function of the saccule and the utricle. All right, so let's look at these projection pathways. Man, I finished it. I did it. This is the last slide. Okay, so vestibulocochlear nerve, the vestibular information comes out, is going to synapse in this vestibular nuclei of the pons, and then it's going to project all over the place. It's going to send radiations to the cerebellum, down to this reticular formation, which are not, it's not important, but the cerebellum, that's going to give you your learned motor skills. For example, Michael Jordan, or I don't know who, God, I know nothing about sports, but some basketball player that you know that is relevant to your life, they have this information coming from their orientation in space, and that is sent to their cerebellum so they can coordinate their learned motor actions. Then these fibers project up to the thalamus, right, which is where they have to project if we're going to be aware of it. There's a synapse there that then relays to the cortex at the visual cortex. All right? This gives us our awareness of spatial orientation and movement. That's it. Great. So I talked about Monday, ocular anatomy, some optics, photoreception. At the beginning of class today, the visual pathways. I talked a little bit about oral anatomy, how the cochlea functions with hearing, the auditory projection pathways. I talked about the basic function of the vestibulocochlear system, balance, orientation and motion, so rotation in 3D and your sense of gravity. And I just flashed through those vestibular projection pathways. Done.